Okay, it's 1 o'clock, so it's time to start the second part of our performance optimization of scientific software webinar series. For those who join us only for this time, my name is Pekka Maninen. I'm an HPC guy here at CSC, the Supercomputing Center in Finland. In the first part, we discussed how to and why should you analyze the performance of your software. And on the second part, we're going to go through some basic ingredients for optimizing the serial or node level performance of your applications. And the story goes or starts from the fact that the CPUs, processors that we are using in our computers and supercomputers are very, very complex devices and ever more increasing complexity. So the CPUs of today consist of multiple cores within one socket. So that's already gives a level of parallelism and also all kind of considerations that we need to worry about when talking about application performance. Also, something called out of order execution have been introduced a couple of years ago already in the x86 processors. So the processors are not they are doing pretty different thing than that we express in the in our program code. So that's maybe quite far away from the what's really taking place in the machine instruction level. Also, the memory hierarchy is quite deep. So there's a lot of levels in making a memory access. So especially something called cache memories. So fast memories, faster than the typical DRAM memories. Also, it's not one instruction per cycle, but these processors are able to do several operations on one CPU cycle. And the performance is very much dependent whether or not you are able to use this single instruction multiple data vector units, SIMD units. And also there's multi-threading capabilities in the processor. So basically the one physical core may appear as two virtual cores or even four virtual cores for the purposes of threading and so on and so on. And in supercomputers, we start packing these CPUs and of course getting more levels of parallelism, getting more levels of complexity. But we're gonna do in this webinar series such that we talk about serial performance this time and things that relate to parallelism on the upcoming third part of the series. And with this scene, so it's very difficult to really operate, or close to impossible to operate on the really the peak performance of the CPU. But without doing anything, we are really harnessing perhaps like single percent or 2% of the peak performance. But with doing some things right, so engineering for performance, minding the underlying hardware, we may be able to increase this percent to 10% with some luck and with the typical compute part algorithm, but that already means may mean already like a factor of 10 in performance. So there's a lot of things that we can do, and especially there's a lot of things that we can sort of underutilize the hardware. So in the following, we're going to discuss how to avoid this underutilization. So how will I write fast code? And to elaborate a bit more on this, the memory hierarchy I mentioned already is that when you are doing an assignment, memory reference. So fetching a value of some address or a variable, well, in practice, a variable means that in order to compute something, they need to be in the registers, and if they're not, they need to be fetched from the physical memory. But just one reference may take like hundreds of cycles. So basically, you are losing hundreds of operations while this one memory fetch is taking place. Of course, it's an entirely different story if you need to read it from disk or scratch or something, or communicate it from another processor. But I just let's focus on this part of the pyramid. So we are in a node where we have physical memory and we have the core. And the key to success here is the utilization of these fast cache memories that are within a CPU die. So close to the CPU core. So they are not in a separate memory banks like this memory as we typically think of, but they are smaller pieces of but faster memories. And really the idea is that the data needs to be copied before they are referenced to these cache memories, such that most of the memory accesses would in fact hit the cache rather than outside of it. And also to elaborate the SIMD vectorization, so single instruction multiple data vectorization I mentioned, is that the CPUs of today are able to perform certain simple instructions on multiple subsequent elements in memory in a one cycle. So on the SISU, it runs on Intel Xeon Haswells. So these vectors are there 256-bit wide, meaning that they can take in 4 double precision numbers or 8 single precision value numbers. So for instance, if you consider, say, summing up 2 vectors, so when using the AVX cycles, we are able to do in a one CPU cycle, we are able to do 4 elements, subsequent elements on the same cycle. If the operation was just scalar operation, so no vectors are used, we are able to do one element plus 1 element equals to 1 element. So 1 element from B, 1 element from A equals to 1 element in C. But in using the advanced vector extensions, we are able to do 4 at the same time. So basically meaning a factor of 4 between a vectorized and non-vectorized code. The current generation of Intel CPUs, so that you can buy today from the market, so Intel Skylake, are able to do already 8 double precision values or 16 single precision values. So meaning that if you go, so factor of 16 in performance is basically bound to the using of the vector instructions. So if you're not able to vectorize your code, you lose a factor of 16, or depends on your personality whether this means that you gain a factor of 16 or lose a factor of 16. So when doing or not doing the vectorization. And as we are in the world of high performance computing, we typically deal with double precision, so the factor is 8 in most HPC workloads. But recalling from the last webinar, so really the key here is that by inspection is pretty impossible to find what's really the bottleneck in your code, and what are the possible inoptimalities in a given code. But you really do need some tools for finding that one out. And the key, or this kind of a fingerprints for single core hotspots can be deduced from this data. So for instance, I can measure the ratios, whether the memory references land, or how big portion of the memory references land on the fast cache memories against as compared to how many of them land outside of it. So if I'm having a miss ratio of several percent, meaning that I'm highly likely I have inoptimalities in cache utilization, meaning that fixing those should improve the performance of the code. Also, I can see from the compiler from the input of the compiler already whether some loops are vectorized or not, and if most of these hotspot loops are non-vectorized, they may be an fruity pick in a way that by fixing the vectorization we should give me more performance on when executing these loops. So I need to combine the data from the performance analysis tool, so finding which are these hotspot loops and combining them with the compiler output to see whether these are vectorized or not. Furthermore, most of the profilers, or I would say all of them, are able to say if separate in the profile if there's a lot of time being spent on math, so expensive math operations like logarithms or exponentials and so on. So different kind of intrinsic math functions. And that's an issue, and there's a couple of things we can do about it. And the remaining of the talk, or towards the end of the talk, I'm gonna present a couple of things for how to fix each of these after we know we have a hunch on possible inoptimalities. Of course, I can go into an extreme details in any of these, but I hope I can guide you a bit further in sort of to get you started, and then you can find more information online and so on. But before going really there, where I modify a code for better performance, let's do a slight detour on something I call optimal porting. And this is something that concerns pretty much everybody using high performance computing systems, because this is something that we talk about when meaning improving application performance without touching the source code at all. So it's not my code, but I need to. Everybody should be still minding performance that such that they port or compile or enable the application that they get to the target platform in a best possible manner. And this means paying attention in choosing a compiler and the flags for that compiler. Also minding that I'm using optimized numerical libraries on wherever I can. Also minor details like how the MPI ranks are being placed across the nodes. If I'm using threading, whether the thread affinities are correct, and also last but not least, how do I use the parallel file system, the cluster file system. But a long story short is that I'm able to do with limited effort some kind of a boost in performance, meaning that from the really sort of an out-of-box performance, I can get non-zero boost on performance, but of course, really reaching the theoretical performance of the selected algorithm needs more effort. But this is something that everybody should do when really doing production runs on high performance computing systems, and should revisit routinely. So this should be kind of a part of everyday life, that we take the applications that we use to the systems in a best possible manner. And a few more words on compilers, because this again this of broad interest in a way. So just a couple of remarks here is that there's a lot of compilers that are able to do high performance or compile scientific applications. For instance, on the CISO system, we have GNU, Intel, and Cray compilers available. And the difference here is that you have kind of different ways of dealing with the code. So they may be replacing some operations with their own intrinsics. They may be using different kind of rounding rules for the floating point math and so on. And one thing to bear in mind is that some compilers are made for more general purpose ones than the other ones. So the default value, how much they optimize code, varies from a compiler to another. But in any case, one thing that everybody should know is that there's no universally fastest compiler. So don't believe if somebody tells you to use a compiler X because that's always the fastest, because it really depends on the programming language, and even with the same language, it's really depends on the application, and in some cases it even may depend on the way you use the same application. So basically input. So that's something that needs to be tested to find what's the best compiler for my given for a given application. And compilers are pretty, I would say, advanced pieces of software. So they are really tuned and developed for understanding the mindset or what the programmer wants to do, and then taking these ideas to the platform as well as possible. So basically, they contain information on the CPU. All kind of very low level things are in the compiler. So the information is the compilers have the information in hand. So these are able to tune many factors and parameters for the microarchitecture that you are targeting, if you ask for that. So it can be compiling for very generic code that runs on any CPU, but in high performance computing, you should always target the CPU that you're going to run on in order to enable this tuning related to the CPU, meaning cache sizes, vector lengths, and so on. The compilers are able to do the SIMD vectorization I mentioned. It's able to exploit these units, but and which of course by more or less by definition should improve the performance. Of course, its hands are pretty tied, as we're going to discuss in the later case. So the optimization here is to help the compiler to vectorize the code for you. And there's a lot of backup tricks in all of these compilers that are able to do different kind of rewrites of your loop. So the loop that you write is not the same as what the compiler after the compiler what's going to be executed in the system. So the compiler likely does some kind of tricks like combining loops or smaller loops, or putting big or then splitting big loops into several smaller loops. It's able to mangle the loop indices. It's able to kind of unroll the loops, meaning that it's sort of kind of an unwrapping or opening up the loops. And the effectiveness of these things varies, but just to bear in mind, the compiler is aware of all of these and tries to do them if the heuristics tell that it's those could be beneficial for performance. And a couple of examples that you can expose when on CISL on different compilers. So always read the man pages of the compilers. So here are the man pages for different compilers that are available on CISL. But some typical flags is that you typically should always go for, with scientific application, HPC application, should target for the as aggressive optimization as you can. So these are typically this kind of an all-out combinations of all-out macros or all-out combinations of loops. Also, you should see that you are always targeting the CPU you're going to run. So on SISU, you want to target on Haswell. If you are running on your own laptop, you want to check with what is the microarchitecture of your laptop, and then target for compiler for that, and don't ever do production runs with generic codes that are able to run, for instance, in all x86 CPUs. So don't be generic, but target always for the microarchitecture. And also, so it's able to give some relaxed precision for speed. It's able to, they are able by some given flags, you are able to get more information what the compiler is really doing, and so on. But just check the compiler man pages for further information. Like I said, the typical behavior is that they want to be, compilers prefer, of course, that everything, or want to ensure that everything is correct. So they're pretty cautious in doing the optimization tricks, even if they know about those. And in scientific software, the algorithms and the case is such that typically you can, in terms of numerics, you can do the all-in approach, throw in all the tricks the compiler knows. And way to enable, well, sometimes this starts giving wrong numbers, or even sort of a garbage, so not the numbers, or something completely random. So if something breaks your code down, your duty is to find the routine that really breaks down because of the optimization, compile that file with less aggressive optimization, and then the remaining of the code with the most aggressive level. So that's really the way to port an HPC application on the system. So take some time, take some effort, but pays off in terms of performance. Also, the compilers are able to be more verbose what they're doing, but you have to request that with some specific flag. And here are the flags for Cray, Intel, and GNU compilers. So, for instance, the Cray compilers on SISU, it's called, or the Fortran compiler in SISU is called FTN. So, enabling the -rm flag will generate an text file that gives an unedited listing of the source code, and so that this is something you need to ask for whenever doing serial optimization of the code. So like I said, they are a complicated piece of software, but doesn't the compiler do everything? No, not yet, and it's been a standard answer for the from the beginning of the compiler. So it's kind of a fusion power that always 10 years ahead of time. And still the fact is that you can make a big difference on code performance by doing something by hand. And I would consider the code optimization, general code optimization is the interplay between the programmer and the compiler, where the programmer helps the compiler to optimize more. Spot optimization opportunities, removing obstacles for further compiler optimization. Using the insight, what should come out, and how do some given arrays or variables should be laid down in memory, and so on. And typical thing to do is really removing some from legacy code, removing some old-fashioned obscure optimizations with the kind of an take-home message is that simple code is the best also for the compiler and performance until otherwise proven. So if you understand what you try to express on a loop, the compiler will understand it as well and make or is likely able to do heavy optimization on it. And really the way forward with serial optimization is to check what the compiler is already doing and then removing one by one those things where the compiler says that the loop wasn't vectorized because of X. So you deal with this reason X. And of course, you should, like mentioned in the first part, you should always optimize only in the places that are meaningful for the total execution time. So do not optimize everywhere, just on the hotspot routines and loops. So use the performance analysis data to establish in which routines are the performance bottlenecks, and also use the same tools for establishing understanding what is really the shortcoming in terms of performance. So is it the cache underutilization, is the vector SIMD vector underutilization, or something else? So this leads me to the code optimization things. So a couple of remarks on how to deal if I conclude that yes, perhaps I should do better in terms of my cache utilization. And some things are that it really comes down to the reusing cache lines. So CPU fetches things from memory first to cache. So, but everything works in terms of cache lines, which are 64 bytes. So every time I make a memory reference that lands outside of cache, one cache line is being fetched, and the 8 subsequent elements are being stored in cache. So you really want to use every time you make this cache fetch, you want to use all of these elements in the same cache line, implying that do always regular access patterns. So indirect addressing is something that's very bad for cache utilization. Also, whenever something is fetched to cache, you want to use it as too early as possible. For instance, and the typical programming tricks are something that you want to block on high-dimensional array accesses, but something that you can assist and control with compiler pragmas and directives rather than by hand. Again, I can't do in this webinar very deep down in this one, but just some keywords for further Googling is really loop blocking and cache optimization here. Also, you sometimes base off of sorting data before operating on it, such that you really can access everything on a regular manner. And things what to consider when designing your data structures of the code, whether this kind of a structure of arrays or array structures are the best ways of laying out the data. And one just like a piece of information for that's typically very often is a really performance issue is that for what relates to cache alignment or cache utilization is how do you deal or address multi-dimensional arrays, and meaning that, for instance, on a Fortran code, you have to bear in mind that the Fortran is column major, meaning that the innermost loop, where the memories are, or this innermost index increases the fastest, or is subsequent in memory. Meaning that if you write this kind of an expression, this is an cache in optimal way, because you every time you may be losing cache lines when doing, because the next iteration is not in fact the next element in memory, but somewhere else. But it's just like interchanging the loop indices in this kind of way may in fact give much better performance in this kind of a case. So the idea is that even this kind of minor details may have a very big impact on cache utilization. And that's something you want to take a look when finding caching optimalities. Bearing in mind that C is raw major in memory. In C, everything goes raw major, and in Fortran, everything goes column major. C memory. Also, there's a sort of an perhaps of minor importance tricks like splitting bigger or bulkier loops in the smaller loops, or fusing multiple small loops in order to improve the cache reuse. But this also, you can assist the compiler for doing this kind of tricks with certain pragmas by providing insight on the loop trip counts. So how big are these loops typically, and so on. Again, something that you may want to take a look just further by Googling for loop fission techniques or loop fusion techniques. Then the next topic was that just drawing ideas for fixing this is how do I then use this SIMD vectorization of that's available on the modern CPUs. And the things relates to the vectorization. So we are now talking about the factor 4 or 8 in performance. So this really is an important thing. And the rules of the game goes such that the compiler will only vectorize loops. So order things in countable loops. So the while style loops won't vectorize, but there needs to be this kind of an for. Of course, you don't have to know the exact number of the how many iterations I'm going to do the loop only at the runtime, but it needs to be a countable loop. And unit writing is the best for vectorization. And well, other rules are that the indirect addressing, so picking addresses from another array, those won't vectorize. If you have, say, branches or function calls within a loops, those may be inhibitors or are typically inhibitors for vectorization. And you can do any recursion in loops. So they on this kind of a simple do or for style loops will vectorize. So you may want to cast things in terms of those in order to do so, rather than do perhaps something that's maybe more powerful in terms of expression or look more elegant, but in terms of performance, this kind of very rudimentary countable loops are the best for application performance. And it's really how to vectorize loops is that see whether the compiler already vectorizes the loop or not from the compiler output, and see the reason why it does not vectorize it. And sometimes it compiles that there's a dependency between two arrays in the loop. So you need to use insight whether the loops do have true dependencies. So can the memory allocations be overlapping, or are there really references to, say, other into the another array as the compiler claims? And if it's not true, the compiler is over cautious, you can force the vectorization with some pragmas like the ignore vector dependencies IVDEP, or using the OpenMP has an SIMD pragma for doing this, achieving or forcing vectorization. or if it's really so that the loop iterations are, or the arrays in the loops are, or on the between the on the right hand side and left hand side of the equal sign or assignment are really dependent. So just accept the situation or try to rewrite it such that you get rid of those things. And if you cannot vectorize the entire loop, so it's by design something that you cannot vectorize, but it may have still parts that could vectorize, and then taking those out of front, they're splitting the loop into a vectorizable and non-vectorizable loop may be beneficial. And an example in here is that I've got a double loop over some arrays where I get a new array in terms of also kind of a stencil operation here. And the compiler tells me that the loop was not vectorized because of a recurrence between old and new, but that's not true. These are completely independent arrays, so they are separately allocated and they are not really dependent on each other. So I can go in and say that tell the compiler that the old and new do not really overlap. So trust me, go ahead and vectorize. Pragma, ignore vector dependencies. So now the loop, the compiler tells, okay, I go in and vectorize the code, and this gives already for this application gives 40% better performance. So maybe just very simple thing to just like encourage the compiler to vectorize more heavily. So and you can see it. This is from the Cray compiler, so you can see it that what it does for loop. So in the first one it was just unroll, and this one it was having the v here, so it was vectorized as well. The last one I want to talk about is something called a technique, is something called strength reduction, and it means reducing the cost of expensive math operation. And this is something relates to the fact that the different floating point operations are really different in terms of cost. So the fastest ones are addition and multiplication. But then everything else starts to cost. So division is already 20 times more expensive than addition. in the same ballpark are taking square roots and reciprocal square roots. And a much more, even like a 5 to 10 times more expensive than these are the, say, special operations like trigonometric operations, exponentials, and so on. And there's also not only the cost of the operation, but also there's some secondary performance considerations related to using these operations. So what can I do is, first of all, try to get the expensive operations out of the innermost loops. So pre-computing some values. So if it's just a constant, then just compute the constant and store it in a variable and multiply with the variable, for instance. Sometimes even pre-computed values in lookup tables may be less expensive. And a typical trick is in optimizing the innermost loops is that replacing divisions by multiplications with the reciprocals can give a significant performance benefit, assuming that you can compute this inverse less often than this original division. And just using insight on the operations, you can deal, or you can perhaps take down some of the expensive operations into less expensive operations, like in this case, the power to multiplications and square roots. This will be less expensive than this operation, or reducing two expensive operations. So perhaps just with this kind of an identity, I can use it, just compute this only with one sinus function as comparison to computing both cosine and sine, of course, of the same operation. Also, some libraries provide vectorized versions of these operations, so you can get rid of those. And again, just have to stress that if these are not the hotspot ones in your code, typically these things may look uglier, and they will generate more code. So of course, if they do not take time in your code, do not do these tricks, because it's just like optimize only where it pays off. And so just like a couple of take-home messages from this tour on things. So stressing that do the performance analysis first, so to know what you're looking for. So do not optimize while writing a code. So do not try to write efficient code. Just write correct and clear code, and then do the performance analysis and see which parts should be optimized. And the modern or the code optimization today is really interplay with the compiler. So whether a compiler is able to do an optimization, and if not, why is that? And is there something you could do fix by rewriting something in a bit different manner? So for the single core performance really raises from knowing the gory details of the modern CPUs, utilizing all of these features efficiently, especially these cache memories, fast cache memories, as well as these vector units. And last thing we addressed was that in fact it does matter how you write your math. So how do you implement equations? Because of these arithmetic operations do vary greatly. What is the cost of them? Okay, I could take questions in this part, so feel free to use the chat for any questions. And I can introduce the lab while waiting. So the our optional lab. So if you're interested, so there's the you can continue with the same code, same instruction sheet as last time, and now do the sections 5 and 6 for trying to optimize the solver provided there. And well, on the last part, it's going to be 2-week break now, and the last one will be talking about how to make parallel codes scale even further. Okay, I don't see any questions. So I hope you give a try with the lab and look up these things on your own time. And the last one is in 2 weeks' time. So thank you for your time, and have a nice week.